Hi, I am Dr. Goodmanson with a rapid derivation video intended for the readers of my book, General Aviation Aircraft Design, Applied Methods and Procedures. In this video, I will show how the hydrostatic pressure equation is used to calculate pressure in liquids. We start by writing the hydrostatic pressure equation. It is derived in a different video. So to explain what we're trying to do, consider this container. It contains some liquid and is open to the atmosphere. Note that it can just as well be inside an enclosed container. We then define the mean or average liquid surface and denote it by the reference line shown. Then let's define an axis for physical dimensions. Let's call it the z-axis, where positive dimensions are above the reference line and negative below. Furthermore, since I already know I will need two positions, I am going to define them right now. Here, Z1 is the position of the reference line at the surface of the liquid, and Z2 is the position of some point of interest in the liquid. Note that the distance between Z1 and Z2 is denoted as h. Most people like to refer to the distance below the surface using the term depth, using a positive value. For instance, they might say that the bottom of the swimming pool is at a 4-meter depth, so h is the depth. Note that this means that the value of Z2 is negative h. Again, what we're trying to do here is to develop an expression that allows us to calculate the pressure at this point in the liquid. Alright, let's focus again on the hydrostatic pressure equation. Let's separate the variables. Then we integrate both sides of the equal sign. Evaluating both sides leads to this. Then let's rewrite this as shown. Now we only need to substitute proper variables. Let's take a look at the illustration. The pressure at the surface is the atmospheric pressure given by P0. Therefore, the value of P1 is P0. The pressure at depth h is denoted by P2, and it represents the expression we wish to determine. You can see we have four variables to consider: P1 and P2, and Z1 and Z2. First, look at the variable P2 in the bottom equation. It is this variable in the illustration. Therefore, let's substitute P for it. Let's omit the variable Z inside the parenthesis for clarity. Next, let's look at P1. It is this variable in the illustration. We will substitute the atmospheric pressure as shown. The term Z2 is simply the negative of h, and Z1 is 0, as shown in the illustration. Let's rewrite the expression using the substitute variables. Therefore, this can be written as shown here. This form allows us to calculate the hydrostatic pressure at any depth h in the liquid. Looking at the equation, we see that the pressure is the combination of two contributions: the atmospheric pressure, whose contribution is independent of depth, and the hydrostatic contribution, ρgh. It increases linearly with depth.